Right, as Jen said, my name's Christian. I use they, them pronouns. I'm going to be talking about this new Julia package and recently submitted paper I have for creating data-driven spectral models. So as we all know, the ability of EPRV surveys to detect small planets is increasingly limited by the challenge of separating true Doppler shifts from apparent Doppler shifts caused by spectral variability. Ooh, next slide. Great. Okay, so for stellar variability, there's time variable stellar features from things like pulsations, granulation, and magnetic activity like star spots. And these can all change line profiles and depths and affect radial velocity measurements. So there's also telluric variability. We also need to account for the imprint of Earth's atmosphere on our ground-based observations. So these telluric features, mainly from oxygen and water, bluewards of 1 micron, absorb and emit their own light. So their column densities change between observations, and this varies the amount of transmission. And if ignored, these telluric features introduce systematic noise across stellar features and can cause large apparent RV signals. So, of course, this isn't a new problem, and many avenues have been explored to mitigate this issue. So you can kind of smartly mask parts of the spectrum with telluric features, like with a Serval or SBART. You can use telluric standard observations although that's expensive in observation time. There are a priori telluric models with line databases like MolecFit. But you can also use information in the data itself to simultaneously model telluric and stellar features, kind of like Woblet or Yarara, or there was another paper that used deep learning and like autoencoders to do this. So the idea for this project was to kind of extend and tweak the implementation of the core ideas in Woblet, and create a method that isn't limited to time variability for telluric spectra, but also includes stellar variability as well as instrumental effects and other kind of like methodological improvements. This joint modeling method and many joint modeling methods rely on the fact that we can separate the telluric spectrum from the stellar spectrum using the Doppler shifting that we get from repeatedly observing the star at different parts of Earth's orbit, as shown here in these simulated observations. So to perform this joint modeling, we built StellarSpectraObservationFitting, or SOOF, which is pronounced like, or SSOF, which we pronounce SOOF like souffle, hence my amateur logo that I made in the top left, which is supposed to be evocative of a souffle, which I realized I maybe should have like had AI make or something, because I only did so good of a job in an hour. But so anyways, this SOOF is like an open source software package for measuring RVs and creating data-driven log linear models for the telluric transmission and stellar spectrum kind of at the same time. So we model this 1D spectrum as measured by EPRV spectrographs at each time as multiplication of a stellar spectrum shifted by an RV with a telluric spectrum. And then this combined spectrum is further multiplied by an instrumental kernel matrix, which approximates a convolution with the instrumental LSF. So this model is fit to the data just by maximizing, multivariate Gaussian likelihood, taking the variances to be the instrumental uncertainties. So kind of talking a little bit more about what these models are, in practice, right? So both the stellar and telluric models are based on this constant spectral template, like the one you see here, with this prominent kind of H alpha feature at 6563 angstroms. So the spectral template is modified with feature vectors that control where the model should vary. So this feature vector W would mostly cause depth changes and maybe some line shape changes in the large line, the large H alpha line at 6563. So in this example, the feature vectors could be multiplied by these scores S, which control how much the spectrum should vary, which creates this kind of linear model in log space. In this case, the scores are causing the line to get deeper over time. So these feature vectors and scores are multiplied together into this linear model, and then they get exponentiated to get how the template should be modified. And so finally, this exponentiated linear model is multiplied by the spectral template to get this overall stellar or telluric model at any given time, which in this case is indeed changing the depth of H alpha and some other lines. As you can kind of see, as it goes from like red to blue, it gets like deeper to shallower. But one question you might have is like, how many feature vectors should you have? And so we slowly build up this SOOF model component by component, starting with only a stellar template. And we see if adding, the first thing we do is seeing if adding a telluric template is helpful, based on AIC. So just because there's parts of the spectrum that are so clean that there's not enough evidence that you should have any even microtellurics. But essentially, we just make sure that the amount adding the telluric template increases model complexity is justified by how much it's improving the model. We then use expectation maximization PCA, which is a form of weighted PCA to find initial guesses for feature vectors that explain high amounts of variance. We initially just used PCA, but we found that it overweighted the variance found at the wings of the orders. So we then kind of keep testing and adding either stellar or telluric components based on which one increases the likelihood more until we reach the desired model complexity. And then we kind of like choose the best model amongst those that we've searched. So kind of like walking through that, because this is a 40-minute talk and not a 10-minute talk. This flowchart kind of shows this example model selection procedure going up to a total of 1 telluric feature vector and 1 stellar feature vector. The notation is such that SOOF kind of 1, 0 is a model with 1 telluric feature vector and 0 stellar feature vectors, but still a stellar template. So that first box on the left, kind of SOOF null 0, where we start, is a model with only a stellar template. And not even a telluric template, hence the null, like rather than a 0. So we start on the very left with the stellar template, no telluric template. And we first ask if that telluric template helps, like should we have SOOF 0, 0 or null 0? It turns out we did. Okay, sure. So we add that component. And now the next question we would ask is which component is better, a stellar feature vector or a telluric feature vector? We make that choice. Turns out that telluric feature vector was better. So we added it in this example. And then in this example, we're just limiting the total model complexity to 1 stellar feature vector and 1 telluric feature vector. So, we would finish just by adding the stellar feature vector. Although we searched up to 5. So it's not this simple of a tree, right? But it gets really ugly if you show up to 5. Anyways, we take this model that's kind of found in the previous step, and we add several forms of regularization to the likelihood that we're optimizing. So this includes L1 norms that encourage model sparsity, L2 norms that reduce model variance, as well as these fast of order n GP terms, which encourage nearby portions of the spectrum to be correlated at line length scales. This regularization encourages the model to be sparse and smooth, as you can kind of see as I flip like back and forth, between these two. You can see that the feature vector gets a lot more clean, and the prominent stellar features become much more obvious. It also significantly reduces overfitting and greatly improves the final RV measurement precision when we do this. So important part of this process is how we estimate model uncertainties. And we can do this in 2 ways. We can first look at the local curvature of the likelihood space around the maximum likelihood estimate. But this slightly underestimates the uncertainty because we're not estimating the full Hessian. So we're not doing the full inverse, and we're losing kind of cross terms in the estimate of the covariance. But it can be done very quickly and is useful for quick explorations. The second way we do it is via bootstrap resampling, where we add additional observation noise to the spectrum and refit the entire model many times to get a distribution of final model parameters. And this enables us to estimate the full model covariance, but it's much slower. But it's useful for getting kind of finalized results that are a little more robust. So we also get bulk RV estimates by combining the RV estimates from each individual one-dimensional order spectrum, ignoring some orders that have RVs with disproportionately high scatter or uncertainties. And if each order model's RV measurements are, independently normal distributed estimates of the same RV, then the maximum likelihood estimator of the RV is their weighted mean. You could, that's not always true, but it's a good approximation. So to kind of test this whole model finding procedure or algorithm, we can try to see how well SOUF is able to recover one of its own models. So we can start just by taking a SOUF model fit to a real set of spectra that has one Telluric or one water-driven Telluric feature vector and one stellar variability-driven H-alpha feature vector. So there will be a lot of plots like these in this presentation where we show the SOUF model components as like flux as a function of wavelength. So the templates, which control the average behavior, will be on the top, whereas the feature vectors, which control where the spectrum vary, will be on the bottom. And so the left plot shows the water-driven Telluric feature vector on the bottom, and the right plot shows the stellar variability-driven feature vector on, its bottom. So to kind of construct this simulated data set, we can multiply these feature vectors by a realistic set of scores for our simulated observations, and then multiply the spectra together to get this kind of, this normalized observed spectrum. We can then approximate the convolution of the input spectra with the LSF instrument, with the LSF function of an instrument. And then finally, we can add photon noise to the observations with, with an SNR profile, kind of taking into account a typical instrumental Blaze function. So kind of going through this analysis procedure for this data set yields some pretty promising results. Well, thankfully, promising results. Firstly, using this EMPCA-based initialization and AIC-based model selection algorithm, we can correctly identify that our final SOUF model should only have one Telluric and one stellar feature vector, matching our input model. So like we showed before, it starts off where there's only, whether or not there should be a Telluric template. And there should be, as you can see in that kind of top little print statement, the AIC goes down dramatically, adding a Telluric template, which you would expect. Going further, adding the next important component is adding a Telluric feature vector, which is controlling that kind of water behavior. And this accounts for most of the remaining variance. It then finds that the next feature vector it should add is a stellar one, and the AIC goes down just a little bit more. But then as we continue adding feature vectors, the AIC starts to go up, basically. So even though it's like, okay, the stellar component, we should add a second stellar component rather than a second Telluric one, neither component is good enough to justify its inclusion. So you can kind of see that the AIC bottoms out at one stellar component, one Telluric component, which is what we'd want, because that was our input model. So all the models that we search are saved along the way, so we can go back and use the minimum AIC SOUF model that has only one of these features in each frame as our model going forward. So after regularization and fitting, our model fits the data down to the injected photon noise level. And this is shown by the bottom two panels. So that green line shows the expected mean absolute deviation per pixel. And on the bottom, it shows the remaining chi-squared per pixel based on the injected photon noise. So the black dots are the actual values, and you can see that they obviously are centered, almost exactly around this green line of what we would expect given the photon noise we inject, which is great. It suggests that we're not, massively overfitting, but we're also reaching the level that we should be, given that we know exactly what we put in. We're getting exactly that, but with white noise. because we injected white noise too. So our templates and feature vectors also match very closely, especially if they're smooth to LSF length scales. And kind of also important is that our photon noise uncertainties that we estimate with this bootstrapping are directly in line with the observed amount of scatter around the true values. So you can see in that kind of residual plot on the bottom, which has the RMS and estimated uncertainties kind of in the legend, our RMS is exactly our uncertainty estimate, which is great. It just shows that our procedure is working as we'd expect. And this is true for both the Telluric scores on the left and the Stellar scores on the right. And maybe most importantly, and critically, this also holds true for the RDs after taking out barycentric shifts. Our uncertainty estimates match our observed scatter, which is good. So we also tested SOOF with NUID observations. So NUID is this is a highly stabilized fiber-fed high-resolution optical spectrograph on the 3.5 meter wind telescope at Kitt Peak. We looked at NUID data from many stars that have all been. We looked at NUID data for many stars, including HD 26965, which is a K dwarf with around 3 meters per second of variability linked to activity indicators. 3651, which hosts an eccentric sub-Saturn, which is useful because it clears out the orbits of smaller, inner planets. There's like stability arguments that should be the only planet, of that period or smaller. And Barnard star, which, is an M dwarf that also has some variability and is an RV standard star. Whatever, that means. There's been some debate, right? But anyways, so just as a note, so SOOF is built to model continuum normalized spectra. So we don't do any, we take the blaze correction from instruments and just kind of like fine tune them with some sigma clips continuum normalization with a quadratic curve. And we also do some pre-processing to like find anomalous pixels and like mask like low SNR edges and stuff like that. But anyways, for 26965, the one with stellar variability, without any knowledge of where spectral variability should be, SOOF, through this model selection procedure, identified many parts of the measured spectrum that are well modeled to the kind of sub% mean absolute deviation, as seen in the bottom panel, with only a stellar template, which is that orange bit at the top. And without a Telluric model, which is why there's just a horizontal blue line. In this part of the spectrum, it makes sense because we're looking at a portion where we don't expect any Telluric features. So that's good, as highlighted kind of in that left bit. There are other SOOF models which do find things, right? So this one was trained on an order of data around 500 nanometers. And it shows our ability to identify and characterize even small Telluric variations. So this kind of GIF, whatever, shows the SOOF model output over time for this small portion of the spectrum around 503 nanometers. And so this is without any help from synthetic Telluric models. We can find and characterize the sub% Telluric variability, as you can see in this kind of small line on the left there. In other parts of the spectrum, SOOF is able to identify and cleanly separate the two primary forms of Telluric variability we expect in the NUID data, namely from oxygen and water. And again, the Telluric and stellar templates are shown at the top, and the feature vectors are shown with offsets at the bottom. Here, SOOF found two significant feature vectors shown in orange and green. The orange vector is very similar to a simulated oxygen spectrum, which is shown below it in pink. While the green vector is very similar to a simulated water spectrum, which is shown below that in turquoise. And not only are the feature vectors in the correct locations, but the scores make sense as well. So the scores, so here we show the same model scores, which is the part of the model that controls how much the spectrum should vary as a function of time. And the scores corresponding to the oxygen part of the SOOF model, shown in orange in the middle, are highly correlated with observation air mass, which is how much sky we're looking through at a given time. And this makes sense because we expect oxygen transmission to be mostly dependent on air mass because it's distributed relatively uniformly throughout the atmosphere. In contrast, the water goes through phase changes in the atmosphere, making its distribution extremely uneven, varying line depth between observations. So the scores corresponding to the water part of the model, which are shown in green, are thus not linked to air mass, but are clearly and independently identified by SOOF in many portions of the spectrum. So other places where there is water, we find scores with the exact same structure, basically. And finding these features here makes sense because we are looking at a portion of the spectrum highlighted in the middle with parts of known oxygen and water bands. So that's good. So SOOF is also able to identify stellar variability in multiple parts of the spectrum. Here, variation in the cores of calcium H and K lines, which are two deep lines shown in arrows, are clearly identified in this yellow feature vector. And another example is the more subtle variation in the magnesium triplet and some iron lines, which are found in the pink feature vector on the right. The scores corresponding to these features track very closely with NUID's directed measurements of calcium H and K, and can themselves be used as activity indicators. So SOOF can also find stellar variability and telluric variability in the same parts of the spectrum. So on the left, we show the telluric portion of a model, which includes a water feature vector shown in orange. And on the right, we show the stellar portion of the model, which includes a feature vector for H alpha, another known stellar activity indicator. And this is the model that we use in our kind of like injection recovery, like simulated thing from earlier, if you recognize it. But anyways, so by combining SOOF models for many parts of the spectrum, we can get extremely high precision estimates for the radial velocity. Here we show the overall RV time series for SOOF in orange, along with NUID's CCF-based data reduction pipeline in blue. The root mean, the RMS scatter and median RV uncertainty are given in meters per second in the plot legends. So our RMS scatter is lower than that of the CCF-based NUID pipeline by around 40 centimeters a second. And our estimated uncertainty is nearly twice as good, around 12 centimeters a second. If you analyze the same data set with Serval, which is a template-based or a template matching pipeline which masks portions of the spectrum with tellurics, our results are right in line with theirs. But we can reach the same performance without any prior knowledge of the locations of telluric lines. So from analyzing 269 and 65, we learned that many parts of the spectrum are simple and can be modeled with just templates, but that also SOOF can identify strong stellar variability, separate the effects of different telluric species, and also separate telluric and stellar variability that are existing at the same time in the spectrum. So for 3651, we will show how SOOF performs on a quiet star whose RV signal is dominated by the effects of a planet. Our RV measurements for 3651 are also excellent and driven by this large known planet signal with similar precision improvements as we had for 26965. And we're again in agreement with Serval's results with around sub 20 centimeter per second single measurement precisions. So our best fit RV planet model using the SOOF RVs is consistent with previous analyses in the literature. When we follow our information criterion-based model selection. So if we add too many model components, we find that some of the planet signal can be absorbed into the rest of the model. But this is not true if you have a reason for choosing how many components you have. So the orange curve is the best fit planet signal, and the blue points are the SOOF RVs phased at the found orbital period. So after subtracting the planet signal, there's only 60 centimeters per second of variability left, which is also consistent with previous analyses. But the 60 centimeters per second of variability remaining is clearly more than can be explained by the 17 centimeter per second measurement uncertainties just based on photon noise. So there's clearly something else there that's not this planet and photon noise. It's probably from the star and other things, right? So, and if you just take the uncertainties from this planet fit based on the curvature of the likelihood space, they are much lower than previous analyses, which estimated the planet parameter uncertainties by scrambling the order of the residuals after the planet removal. So we use GP Linear ODE Maker, or GLOM, which is a package for modeling multivariate time series with a combination of a latent GP and its derivatives, like PyNeti or S+Leaf, if you've heard of those, to jointly model the RV variability along with variations in H alpha to create a more realistic model for the remaining variability. So in addition to being a more realistic model, it also produces much more plausible uncertainties for the final planet parameters. So from 3651, we learned that while AIC-limited SOOF models don't affect planet signals, model selection is important because using an arbitrary amount of feature vectors can absorb planet signals. And activity indicators can be used to further decrease the effects of stellar variability in the time domain, as we maybe have, I'm sure has been addressed at some point in this RCN series. So finally, let me just check how much time I have. Okay, I have plenty of time. So finally, we analyzed Barnard star, which shows how SOOF performs on an M dwarf with much lower flux and whose RV information content is primarily in the redder wavelengths. So SOOF can find and separate stellar and telluric variability in the same part of the spectrum, even with 4 times less signal to noise than 26965. And just like 26965, in this part of the spectrum, we found water variability in the telluric model on the left and H alpha variability in the stellar model on the right, along with some variation nearby calcium 1 line. So both SOOF and Serval measurements, both SOOF and Serval's RV measurements for Barnard star have slightly lower RMS scatter than Newid's pipeline, but they both have nearly 7 times higher precision. This discrepancy is largely due to the default CCF mask for Newid's DRP, just not using a significant portion of the Doppler information available. So from analyzing Barnard star, we can learn that SOOF can still identify stellar and telluric variability even in the low SNR regime. It can also reach high precision for M dwarfs. So just kind of like wrapping it up a little early. From all these stars, we've demonstrated that using only this high resolution 1D spectra, and critically without the input of synthetic spectra or line lists, SOOF can recover EPRV measurements with state-of-the-art precision accuracy and produce data-driven models for the deconvolved and time-varying telluric transmission and stellar spectrum. These models can provide a powerful way to generate synthetic data sets, including both stellar spectra and telluric transmission with arbitrary RV signals like the toy model that I showed earlier. These can also be used for evaluating SOOF, other EPRV pipelines, or any other stellar variability modeling tools. SOOF is effective on multiple spectral types, with or without the presence of a planet, and with various levels of known stellar variability. So some of the things that we are currently working towards are incorporating telluric model priors, just because you can relearn where oxygen and water are based on the data. You don't necessarily have to, right? We have lots of data on where we expect features to be, and we should use that, if we can. So we're also working on applying this pipeline to additional instruments. I've already used Express data on it, and this pipeline is built to be instrument agnostic, so it's not it's not super complicated to make this useful for other instruments. It's mostly like a data formatting thing, but we just haven't yet for a lot of them. And finally, and maybe the most useful thing, maybe the most useful thing for us at least is that we're working towards automatically analyzing like all of the new at nighttime targets with this pipeline, and we're like halfway-ish done. I don't know, Eric Ford, who I was working with, or I guess am working with still, might disagree with that rough calculation of how close we are to finishing that, but we've made significant progress on it at least. So with that, I will leave you with my conclusions, and I'm happy to take questions.
Awesome. Thanks for a great talk, Christian. So I will keep an eye on the participants list. If anyone has any questions, please raise your Zoom hand. Nathan.
Hi, Christian. Thanks for the great talk. I was wondering, once you have found a planet, is it something that you can use to go back to the spectrum to reanalyze, and would that provide a valuable information or not?
So you're saying if we have a target with a known, oh, wait. Okay. Are you saying like for 3651, can we take out the RV from the known planet and kind of like almost go back and be?
Yeah, that's it. Yes.
Yeah.
To have some sort of iterative procedure, and if you expect that it would make the procedure more precise somehow.
Yeah, so I wouldn't think so, just because, you know, we're already taking out like a known Doppler shift in the, you know, barycentric like correction, right? So in my head, it would just be like, oh, consider this to be part of the barycentric correction, but like you still would be measuring the relative RV to whatever you're, you know, setting it to. Like you still have to do interpolations or whatever, like I don't know how much you would gain from being like, this is an extra known part, you know, unless you were also fitting, like you had like a GP term, you know, like a stellar activity, basically GP or something that you added to the likelihood, and you said, okay, take out this planet portion, right? Like you could add time domain features to the likelihood, in which case then taking out the RVs would be helpful. But as it currently stands, there's no time dependent terms in our likelihood function. So taking that out, I don't think would do that much. But maybe we can email about it as well.
Thanks.
Bryson.
Hi, Christian. Yeah, great talk. I had like 4 questions, but I'll just start with one and let others ask the questions as well. So a simple one, what's like the average like runtime for like, say, like the whole Newitt bandpass and some reasonable number of observations on a reasonable machine?
Yeah, so it depends on how much you want to do, right? So like kind of minimally, if you are like, I want to, given this spectrum, I want to initialize a model, and like, but give it, say I'm like, I'll initialize the model, but I know what regularization I should use or have a guess for it. And like, I only want to do a fast uncertainty estimation, you know, then each order for like 60 observations takes, I don't know, 10 minutes or less. But if you want to learn what regularization you should use with cross-validation, and you want to, you know, do the bootstrapping for the uncertainty estimation, then each order can take like an hour or something if it has, you know, multiple, you know, if it has multiple feature vectors. So it just kind of, it depends on how much you want to do. But yeah, no, the access to a supercomputer for this project was useful. For iterating through, right, and being like, does this make sense? Does this work? Yeah, so it is not necessarily I'm going to put this model on my laptop and apply it to my data set in 2 minutes sort of thing, unfortunately.
Yeah, gotcha. Yeah, thanks.
I've got one while we wait to give other people a chance. So Christian, could you comment a little bit more about the stellar feature vectors and what you see in them? Do you see any future prospects for interpreting those to like find new activity sensitive lines or dig down more into which parts of the lines are most sensitive?
Yeah, for sure. I mean, I definitely kind of view this as being kind of in concert with a lot of the like line by line work that's being done as well right now, where, they're associating, especially with like, FF prime sort of frameworks, you can be like, is this a convection line, or is this a, whatever else line, or, photospheric line? But yeah, I mean, I think that is a very useful byproduct of this, is that it's extremely, well, it's as interpretable as any other, model, right? Like it's not it's not like a deep neural network where you're just like, oh, I don't know. Like you can be like, oh, it's this, this is where, the flux is, right? This is what is happening. So I think someone with more kind of stellar atmosphere and chemistry and other quantum whatever transition experience than I do could view this as a very rich data set for, oh, this star of this temperature, this log G, this whatever is varying here, right? Like this is where the data says it's varying. So yeah, I think it is a promising way forward for someone who wants to do a PhD in that.
Totally, yeah. It's interesting you mentioned like that this could be specific to a star of a certain temperature, gravity and stuff. I wonder if it would be cool to get the feature vectors for stars of different spectral types and try to see if there's like a continuous change between them or something.
Yeah, I did. I think I wrote at least one proposal to do something like that, where that was like a very much a stretch goal, because, like it would take a lot of, compute and like a lot of data sets to really fill out the, n-dimensional space that is, like stars, right? But no, I think it is super, super interesting, and definitely a really cool thing to work towards.
Totally. And Eric Ford is recruiting possible interested participants in the chat, so reach out. Bryson.
Yeah, if no one else has questions, I'll try and ask another one here. So correct me if I'm wrong, Christian. So it looks like there's no explicit air mass correction used in for the Tellurics, or nothing to account for the air mass correction. So you just throw that into the Telluric feature vectors. Is that correct?
So yeah, the model doesn't know about air mass at all. So it can be independently found, right? It's like, oh, there's this weird portion of the spectrum where the lines dance in this way, and the answer is it's oxygen dancing to air mass, right? And so we can be like, oh, that's, we could get an independent estimate of what air mass should be. But yeah, the model itself doesn't know about air mass at all. But it's one of many avenues to explore. It's like, would this, I mean, I don't think it would improve the model performance that much, because essentially it's just like a scaling. Like it would still have to find all of the features, on its own, which is kind of the harder part anyways. But yeah, so the answer is it doesn't know about air mass, but it can figure it out, which is cool.
Yeah, sounds good. Yeah, thanks. It's interesting that it's able to do that all on its own.
Yeah, it's I think a testament to our excellent instrumentation as well. Shout out to our observers and instrumentalists.
I'm going to abuse the power that Jen has vested in me and ask you one more question.
Sure, go for it.
I think that so there's a lot of improvements in this over the some of the framework that like Wobbly established that was similar to this. But one of the big ones that I think is a lot better is that you explicitly include the line spread function in the model. Have you tried or thought about allowing the line spread function to be time variable? And would this be a viable pipeline to use for less stabilized instruments?
Yeah, so something that's really interesting in how we've set this up is that including LSF information, either just one, right, saying it's constant at all times, or having a different one at all times I think it's like, it makes the performance like it's like 15% slower at the most or something if you go from no LSF to like having a different LSF at every time. So we don't fit the LSF, but it's very easy to if you have it characterized, you know, independently, to throw it in, you know, with arbitrary functional form. So it's definitely a possibility. We, you know, the way we did it is we just like we said it was constant every time just because we didn't like measure the LSF right at every observation. So we, you know, I'm sure that gets you like 90% of the way there is like having an LSF in the first place, right? But no, it is very much, it is totally within the framework to have a time variable LSF. Like that is not a problem. I think the bigger problem is like actually getting the LSF data right and being like because we have no machinery for fitting it, right? Kind of partially because historically it was such a degenerate problem that, you know, it was found to like limit things to like the meter per second level if you were trying to like fit the LSF and the Stellar, you know, template and the Tellurics all at the same time, which is kind of like, I wish I could say which is why we didn't do it in the first place, but I mostly found that out researching my introduction for my thesis. But it is at least a justification to say it's possibly not worth the development effort to try to do all three of them at once. But yeah, if you can characterize the LSF on its own, we can accept a different LSF at every time, which is nice.
Yeah, that's great. Thanks. Any last questions for Bryson?
All right, this is my last one. So your GP regularization is really quite like awesome, and like how it's like very like motivated by like the actual lines of the star, and like how maybe wide they are and how close they are to each other. But I'm curious if you ever tried like maybe something even simpler, like before the GP regularization, did you ever try something like Tikhonov regularization where you're just looking at the differences between each neighboring point or something like that?
So we definitely have thought about the almost having like a primitive like acceleration regularization, right? Where you're like, oh, you know, this data point should not be drastically jumping and then drastically jumping back. It is, I don't remember if I ever coded it up and tried it. It was definitely on my radar, but I think I just like leapfrogged it, where I was like, oh, well, we could just say that nearby data points are correlated, and this is like a more, you know, I was like, there's machinery to do something more complicated, and I was like, I want to try that. So I think it came up as an idea, and then I was like, but I think I can do a GP for this. So yes, it came up, but I don't know if I ever actually implemented it and tested it out.
Yeah, gotcha.
Yeah, I instead wasted like 3 months of my own time trying to code up a fast GP framework instead.
That's right. I'm sure it was well worth the learning experience either way at the
Yeah.
end of the day. Yeah, thanks. Very cool.
Okay, if there's no more questions for Christian, let's thank the recently minted Dr. Gilbertson again for a great talk. Oh, sorry, Nathan, did you have a question?
No, I just wanted to upload. I
Oh,
I hit the wrong button.
one. All right. Well, thank you so much, Christian.
Yeah.
And see everyone next month.